Thank you, viewers. This is Mr. Odingo, and today we want to learn how to prepare alkanes in the laboratory. In our previous lessons, we were able to talk about nomenclature of alkanes and also what we refer to as isomers or isomerism. Before we talked about isomerism and also nomenclature, we described Introduction to Organic Chemistry 1, where we talked about hydrocarbons, and we said hydrocarbons are those compounds which are made up of carbon and hydrogen only. Now we have moved far. We understand what alkanes are. We know how to name them now. We know what isomers are. We want to know how to make alkanes in the laboratory. Now we want to make alkanes using a method called decarboxylation. Decarboxylation. Now decarboxylation, we want to understand what is decarboxylation. When you are preparing alkanes, we need a metal alkanoate. For example, sodium alkanoate. When I talk about alkanoate, I talk about organic salts and using soda lime. Soda lime is a mixture of sodium hydroxide and calcium hydroxide. Now in this particular compound, we have now sodium propanoate in this case reacting with soda lime, and the only thing it will react with is sodium hydroxide. So calcium oxide here is just using as, we know calcium oxide is hygroscopic, or not hygroscopic, let me say, yeah, hygroscopic. Hygroscopic because it absorbs water. We know that water from moisture or water vapor from the moisture can be absorbed by sodium hydroxide, and whenever this sodium should be used in solid form. If it absorbs water, it will be wet, and that is going to cause a problem to us. So instead, we need to have calcium oxide here, which is going to keep this sodium hydroxide dry by keeping away the moisture from air. Now, I've said that this process, when you react sodium propanoate, we said that it's going to react with sodium hydroxide, not calcium oxide. But what we need to use is soda lime, which is a mixture of both of these two. But I've said that in the reaction, only sodium oxide reacts. So if we are reacting this sodium propanoate, that is C2H5COO. Na. This is sodium propanoate. Propanoate because there are 3 carbon atoms here, or we can say it is C3 if we do it this way, CH2. This is sodium propanoate. If you react this sodium propanoate with sodium hydroxide, what we are going to get is, we are going to get ethane. Ethane is C2H6 plus sodium carbonate. So it means that if you look at this thing, it's like the acid that was used here is an acid with 3 carbon atoms, 1, 2, 3. That's why we call it propanoate, sodium propanoate. But when you come to this alkane we are forming here, it is an ethane with only 2 carbon atoms. So every time you are making, or we are doing this particular process, you need to ensure that the salt you are using, the organic salt you are using, has one more carbon atom than the alkane you want to prepare. So for example, if I want to make methane with 1 carbon atom, I will use the salt with 2 carbon atoms, meaning I will use here, instead of sodium propanoate, I will use sodium ethanoate, which is CH3COO-Na. This is sodium ethanoate. Now this sodium ethanoate, if you add sodium hydroxide from soda lime there, what you get is methane CH4 plus sodium carbonate. So you see that the methane we are forming in this particular case here has 1 carbon less than the salt, the organic salt that we had here. This salt had 2 carbon atoms, and then we are getting methane. It means that if we use sodium butanoate, we are going to form propane. So every time the salt must have one more carbon. So propanoate, sodium propanoate, ethane. Sodium ethanoate, methane. Sodium butanoate, propane. Sodium pentanoate, butane. So we have to take one with the one carbon ahead. Now, this equation here, I believe, is balanced. If we have this one, C3, 2, 3, oxygen 1, 2, plus this one 3, carbon 1 here, plus the other one we have counted already, hydrogen, yeah, it's okay. It's self-balanced. By just reacting that, the equation is self-balanced. So this one here is, we have here, like in this case, for us to form ethane, I used ethane as our example here. We used sodium because ethane, we said ethane has 2 carbon atoms. The salt must have 3 carbon atoms. The organic salt of sodium with 3 carbon atoms is sodium propanoate. So this is sodium propanoate plus. This one we said is soda lime. But in your head, you just know that soda lime is a mixture of sodium hydroxide and calcium oxide. But in our equation, only sodium hydroxide is taking part in the reaction. The soda lime is actually helping us to ensure that this sodium hydroxide remains dry throughout the reaction. So sodium hydroxide here, we said we get ethane plus sodium carbonate. You remember when we are talking about features of homologous series, we said that all members of homologous series have the same method of preparation. And we can be able to see today here that what we are going to use to prepare this salt is just the same. We are using metal alkanoate and soda lime to prepare all of them. Only that when you are selecting the salt to use, we must bear in mind that the type of alkane we want to make. If you want to get the first one, which has 1 carbon atom, the salt here must have 2 carbon atoms, you can see. If you want to make ethane with 2 carbon atoms, we have to use a salt with 3 carbon atoms, 1, 2, 3. If you want to make a alkane with 3 carbon atoms, that is propane, is having 3 carbon atoms. So we have to use a salt with 4 carbon atoms. 4 carbon atoms, we know that I can say CH3H7. Why do I put 3 here? Because I know that 1 carbon atom is going to be in the functional group here. So I will start with C3, then COO-Na. This is sodium propanoate. So you can, if you want to know the total number of carbon atoms, take this one here plus the one in the functional group, you get 4. Then plus sodium hydroxide in the soda lime. Then you get, when you are reacting this, we know we are going to get the alkane with 4 carbon atoms. That is C3H8. Sorry. We said that if this is 4, we are making alkane with less carbon atoms by 1. Then plus sodium carbonate the other side. Yes, so you realize that this is what is forming for us propane. This is what is forming for us propane. It means that if I want butane, what do we need to do? We need to use sodium pentanoate. So we have to take a salt with 1 more carbon atoms. Now this is the setup that you need to use when you are preparing alkanes. And in this case, we were preparing ethane here, which we know is a gas. And this gas, we know that is insoluble in water. That is why we are passing this gas through water. So once you heat this mixture here, sodium propanoate, a mixture of sodium propanoate here with soda lime, what is going to take place is this reaction here. So once this reaction takes place here, we know that sodium carbonate, a solid, will remain here, but ethane is a gas which will evolve passing through this tube to this particular part. And since we know it's not soluble in water, we can collect it by our water collection method, and our gas will be collected up there. You cannot see it because this gas is colorless, so we are going to see the gas being collected there because it's not colorless. So viewers, that is how you prepare alkanes in the laboratory, and as you can see, these alkanes are easier to prepare. What you just have to put in your mind is that when preparing them, we need to add a metal alkanoate plus soda lime to give you alkane plus sodium carbonate. Another thing you have to put in your mind is that the ethane you have to prepare, if I want to prepare an alkane with 2 carbon atoms, the salt I'm choosing must have 3 carbon atoms. If I'm getting a salt, an ethane with alkane with 10 carbon atoms, I have to choose a salt with 11 carbon atoms, and those salts we have said they are called metal alkanoids. In this case, we use sodium alkanoids. So viewers, we are going to go to the next thing. We are going to look at the physical properties of alkanes. So the physical properties of alkanes are very simple. We are going to look at a few features. While the physical property will start with density. After that, that's number one. Second one, I will speak about melting and boiling points. Melting and boiling points. Number three, we are going to talk about number three, yes, we are going to talk about solubility. So viewers, when we talk about these substances, what I want first of all to tell you that initially I talked about density earlier. I talked about density and I told you that physical properties, these are the things we can see, measure, not just see, observe. The word observe in chemistry or in biology means something you can really feel using your 5 senses. Meaning you can see, you can hear, you can taste, although in chemistry we are told not to taste anything. We can smell, we can feel by touching. Touch. So anything that these things can tell, that is a physical property. But it goes beyond just 5 senses. It goes up to things we can measure. You can measure anything, you can measure length, weight, mass, anything measurable is going to fall under physical property. Like density, a density is coming from mass and volume. We know we can measure mass, we can also measure volume. Density is a derived quantity. So we derive density by calculating mass divided volume, but both mass and volume can be measured. So all that, what we can measure and combined with other 5 senses falls under physical property. So we want to look at density here. And I said before that density is equals to mass over volume. Is equal to mass divided by volume. So I want to directly compare density and mass. So density is directly proportional to m if we can see. It means that if m is more, the density will also be high. So we know, we remember last time when I talked about introduction to organic chemistry, I mentioned something to do with moles. And in moles, you're able to calculate what we call molar mass. Molar mass is the mass of 1 mole of a substance. So if I have ethane, which is CH4, methane, which is C2H6, C3H8, these are the substances here, the first 3 members of alkanes. Now you see that if you want to calculate the mass, this is 12 plus 4, which is 16. This one is 24 plus 6, which is 30. This is 36 plus 8, which is 44. So the molar masses of these particular molecules or alkanes from number 1, 2, and 3 is 16, 30, and 44. Now 16, 30, and 44, like I said, density is equal to mass over volume. In this case, we have our masses, and we have said also that density is directly proportional to mass, according to this equation. It means that the bigger the mass, the higher the bigger the density as well. So it means that this methane with the mass of 16, mass per mole of 16, the density will be smaller compared to propane, which has a mass of 44 per mole. So we can say therefore that as the number of carbon atoms increase, also as the molecule becomes bigger, so does its density. And how can we tell that? This one has 1 carbon atom. We know that carbon is responsible for the bigger percentage of this particular compound. So as we increase the number of carbon atoms, meaning as we increase from number 1, number 2, number 3, number 4, the densities will also increase due to the fact that density and mass are directly proportional. Now, other than density, we have talked about melting point. melting and boiling point. Melting and boiling point, just like density, we cannot say that this is the melting point or this is the density, because these things are not the same. This is a family. Alkanes is a family. It's a family of very many molecules. We are just going to show the trend. Like I've said, density, it increases with increase in the size of the molecule. So as we come from the first one to the second one to the third one, I know when I say the first, 1 carbon atom, the second, 2 carbon atom, the third, 3 carbon atoms, the density will also increase. So one with the bigger size like decane with 10 carbon atoms will have a bigger density than methane with 1 carbon atom. When you come to boiling and melting points, we have to first of all understand simple molecular structure, where we said in simple molecular structure they have what we call van der Waals forces. Van der Waals forces. Van der Waals forces is the sum total of the interaction of the covalent bonds, the forces between atoms in this particular molecules. So we know that this is methane, but this methane is connected to another methane molecule via what we call weak van der Waals forces or intermolecular forces of attraction. So the intermolecular force of attraction here will become stronger as the size of the molecule becomes bigger. So that one we are saying that if you look at this one, that's why we realize that the first 4 members of this particular alkanes are gases. But from there you'll change to liquids, then liquid changes to solids later on. So why are they changing like that? Because the intermolecular force of attraction between molecules will always increase with the increase in the size of the molecule. And the size of the molecule will increase by CH2. We talked about this one before, that it is like a series and sequence, that from the first member, if I want to get the second member, I add CH2. I want to get the next member, I add CH2, like that. So this will be the additional from one member to the next. Consecutive members, you add CH2. For example, methane is number 1 with CH4. If I want to get ethane, I will add, C will be now 2 if I add CH2. So it will be C2 now, because this is C plus C, 2, alafu 4 plus 2 is 6. If I want to get there, I simply again add CH2. So CH2 there, this is C3H8. So this is what, as this one is added, when this one is added here, the force of attraction in ethane here will be stronger than the force of attraction here. So in terms of melting and boiling point, ethane will have a higher melting and boiling point than methane. And propane will have the highest melting and boiling point in this among these 3 molecules, because since the size is bigger, the forces of attraction holding the molecules are very strong, which means that it requires more heat to overcome here than the amount of heat required to overcome here. So that explains why when you talk about substances like pentane could be a liquid. We know when we talk about crude oil later on, we are going to meet pentane as part of what we call petrol or gasoline. So at that particular point, you have liquids which are highly volatile, then they become less volatile as you move to the solid part. So they change those states of matter because decane, for example, which is expected to be solid, decane is actually maybe a very thick liquid. Decane is having 10 carbon atoms. Being the molecule of decane is very big, so the force of holding the decane molecules will be very strong because the size is increasing. This one is something we have mentioned before in what we call covalent bonds and intermolecular forces. So that is up to boiling point. So generally we can say that the trend in the melting point is that the melting point will increase as the number of carbon atoms increase in a molecule. And the melting point and boiling point are compared the same way. As the melting point, so will the boiling point increase. So we expect decane to have the highest melting and boiling point and ethane to have the lowest. So it's a trend. We cannot say a particular figure that the melting point is this particular figure. Now the third one is solubility. Solubility, like we have said before, substances, and I mentioned this in covalent bonds. Covalent bonds do not dissolve in water because these substances are not ionic. Water is polar solvent. water is polar solvent, it can only dissolve a polar solute. But these alkanes are not polar solutes. So it means therefore that water cannot dissolve alkanes, and therefore we can simply say alkanes are nonpolar and can only be dissolved by nonpolar solvents. It means that alkanes can only dissolve in nonpolar solvents. Nonpolar solvents like propanol, all those things that are nonpolar can dissolve that one. But when you talk about polar solvents like water here, it cannot dissolve alkanes. So what we can say that alkanes will dissolve in nonpolar solvents like alcohol and so on. Alcohols are very many. Then we have what we call propanols and so on. Those ones will dissolve there. But when you come here, they cannot dissolve in water because, like I said before, water is charged. Water is charged. If you have this is water, that's water. This one is partially charged. This also partially charged. This one also partially charged. Partial negative charge. That's why there's what we call hydrogen bond in water. So the presence of that hydrogen bond, because this one is having what we call high electronegativity. Electronegativities of oxygen and hydrogen here are not the same. We can understand what I said about that. When electronegativity of one atom to the other are the same, then we expect we are going to form what we call a pure covalent bond. But when the electronegativity of oxygen in this case is bigger than this one, we expect that we are going to have what we call hydrogen bond, and we know that hydrogen bond causes what we call positive and negative charges, meaning that water can dissolve only polar solutes like sodium hydroxide, sodium chloride, calcium chloride, and so on. But when we come to nonpolar solvents, they can only dissolve alkanes because alkanes themselves are nonpolar. We have said they have what we call weak van der Waals forces holding the particles. So again, now when we compare the solubility here, the solubility in this case here, we have to know that the molecule with the smaller size will dissolve more quickly than the molecule of the bigger size. We have to know that we are still going to refer to what we call the forces of attraction between the molecules. The force of attraction will play some part in solubility. If it is weak, it can be solved quickly. But if the force of attraction are stronger, then it will take time to dissolve. So it means that methane here will be dissolved quickly in something like propanol. Propanol will dissolve quickly in a propanol than pentane can dissolve. Because pentane, we have said the molecules holding pentane molecules are very strong compared to the force of attraction holding, the weak van der Waals forces holding methane molecules. So methane molecule will dissolve much faster. So basically, as I conclude this part of physical properties, what we have to know is that alkanes do not dissolve in polar solvents like water, but they dissolve in nonpolar solvents like propanol, and alcohols are also, other alcohols are also polar solvents. Now that we have understood physical properties, I want us to go to what we call chemical properties. And the chemical properties of alkanes, we are only going to talk about two mainly. These two chemical properties include burning or combustion and also substitution reaction. So this is chemical properties. So I said that physical properties include things that we can see, things that we can tie our five senses, and also things that we can measure. But chemical properties involves how these alkanes react. They involve reaction. Chemical reaction, we know that the product and the reactants are totally different, and usually sometimes they are irreversible. So the first chemical property here we want to talk about is combustion. And combustion meaning burning in oxygen. Combustion of alkanes. How do alkanes burn in oxygen? Oxygen here we can also say in air, because air has oxygen. So we have two types of combustion. We have what we call, let me say types of combustion. We have two types of combustion. And these two types of combustion, number A, I will say we have what we call complete combustion. Complete combustion, and number B will be incomplete combustion. So we have these two types of combustion, and I want to explain both of them. Now, complete combustion occurs when there is sufficient amount of oxygen. Complete combustion. Complete combustion. I've said that this complete combustion occurs when there is sufficient amount of oxygen. So there must be sufficient. Sufficient meaning enough. Sufficient amount of oxygen. So if oxygen is enough, it means that the carbon atoms in the molecule can completely burn to produce water and carbon dioxide. During that process, there will be a lot of heat produced also. But heat has no chemical formula, so we cannot include heat as one of the products. So we are saying that if we heat alkane, if we burn alkane, not just heat, but we burn alkane in oxygen, I've said that we are going to form water and carbon dioxide. Water and carbon dioxide, or what we call carbon 4 oxide. That is what we are going to get. So basically what we know that this is very important. This is very important. We remember at home we use what we call LPGs. LPGs, these are liquefied petroleum gas. Liquefied petroleum gas are the ones we use to cook at home. They are actually alkanes, because when you burn them, when you burn these alkanes, when you are cooking with them, you produce water, carbon dioxide, plus some heat energy that we need. Actually, in this reaction, we just need the heat energy, not water or carbon dioxide gas. So I've said that in this case here, oxygen must be sufficient. Oxygen must be enough or more than enough so that all the carbon in the alkane can burn. So that if I write an equation of ethane, for example, burning in oxygen, what will I get? As I said, I will get carbon dioxide and water. Once you write it like this, the only thing remaining for you is to be able to balance the equation. So if I balance here, carbon, if I say carbon is 2, how many here? So carbon is 2, how many hydrogen? 6. So if I say this is hydrogen 3, this is 4 plus 3, 7. 7, I can say this is 7 over 2. Now, you can balance the equation like this, or you can simply remove this one by multiplying everything by 2. It means that if I multiply everything here by 2, I will get here 2, but this one will be 7. Then this one will be 4. Then this one here will be 6. So this one is a balanced chemical equation for the reaction between ethane and oxygen to form carbon dioxide and water. This is what we mean by complete combustion. So in complete combustion, the products are carbon dioxide gas and water. You realize that when you burn this completely, you will produce a blue flame. Usually when you see a gas cooker, when you open, there's a time when you open the air hole, you make the air hole become very big. What happens is that the flame turns yellow. Yellow, sooty flame. That one means the carbon that time is burning incompletely. But when you put a small flame, it's very steady, it's very hot, and it's blue in color. That means there's complete combustion taking place. And that particular moment, you realize that the sufuria or the whatever you're using to cook there will not turn sooty. That means you are doing what we call complete combustion. Remember, this combustion can take place both at home when you are cooking, lighting, or sometimes in the engine of vehicles. There's also combustion taking place to produce energy that will make the vehicle or the machine move. So that's what we mean by complete combustion. Complete combustion produces carbon dioxide gas, and we know that there's a problem with carbon dioxide gas is what we call pollution of air, especially global warming. That is a problem of carbon dioxide gas, because carbon dioxide gas has a tendency of absorbing long wave rays. These long wave rays, they are weak, so carbon dioxide can absorb them, creating what we call some excessive heating of the surrounding. Now, we have talked about complete combustion, but compared to incomplete combustion is better. It's better to have complete combustion than incomplete combustion. So, I've given you an equation here. Methane can go under the same equation. Propane can undergo the same equation. But what you have to know, stick to the products: water and carbon dioxide gas. That is how you know there is sufficient oxygen. Now let's look at what we call incomplete combustion. Incomplete here meaning that combustion is not taking place fully. It's not taking place fully because something is missing. Now, something is missing. That something that is missing is usually oxygen. Oxygen determines, the amount of oxygen determines whether we are going to have complete or incomplete combustion. Complete or incomplete combustion. Now, incomplete combustion, because we said that there will be insufficient oxygen, it means that the carbon atoms in the alkanes will not be burning fully. Some will be going out unburnt. And those unburnt carbon will produce sparkling. When they meet the flame, they sparkle brightly. That's why they are used to as for lighting. You see that a candle or that lantern lamp that we use at home is actually undergoing incomplete combustion. And that is how it can really illuminate the house, because the flame coming is yellow and sparkling. The what sparkling, there's atoms of carbon passing through the flame and giving that particular shiny that reflects in the house to be able to give us that particular light. So it's like that because some carbon is not burnt. When you use that flame to cook, it will leave soot. It will leave soot or smoke. Soot will stick on the surface of the sufuria. Smoke can be sometimes seen going out as black something or dark. It's dark because carbon is black. So those are carbon atoms sticking. Carbon atoms that were not burnt into carbon dioxide. So if we now write equation, we are going to say when you really do incomplete combustion, I've said that that happens if there's insufficient amount of oxygen, if oxygen is not enough. If you burn and there's insufficient amount of oxygen, you are going to produce carbon monoxide and water. So in incomplete combustion, if I have alkane burning incompletely, and I said incompletely meaning that this oxygen is limited or insufficient. Let me use the word insufficient to give us carbon monoxide or carbon 2 oxide. Carbon monoxide and carbon 2 oxide are the same. Carbon 2 oxide and water. So you can see that the only difference between what we had before is this carbon monoxide. The other side is carbon dioxide. But you also realize that the other one will be hotter because all the carbon are burnt. So there's more heat energy produced. But in here, some carbon are unburnt and therefore some energy is not actually given out. So if we write an example of ethane C2H6, ethane burning in oxygen, and we say that this oxygen is insufficient, we are going to get carbon monoxide, which is CO plus water. So CO plus water. If I try to balance this equation, if I say carbon is 2, hydrogen is 6. This is 6, so I'll say this is 6 here. So this is 3 plus 2 is 5. I can say 5 over 2. Like I said before, if you don't want to use fractions in this particular case here, you can simply remove the fraction by saying this is going to be 5, this is going to be 2, this is going to be 4, and this is going to be 6. This one now we have an chemical equation without, this is a gas, this is also a gas, this is also a gas, it's a liquid. Now, we know that a word equation, some of us like writing word equation. This is ethane here. This is oxygen. But we know that this oxygen is insufficient. That is why we are getting carbon monoxide. Carbon monoxide or carbon 2 oxide. And then what we are having there is water. So you see what we have here. We have this reaction that is occurring incompletely. I've said that this reaction here produces soot. Now, we know that soot is bad. Whenever you see soot, it means 2 things. One, there was some carbon sticking in that particular substance. If it is the wall of a house, it will become dirty. If it is sulfuria, it will become black and dirty. And also, you know that some energy have not been released because some carbon are actually not burned. Under what circumstances will this occur? We know vehicle engines. Vehicle engines are put in very tight spaces where there's not enough circulation of air. So usually you'll have some form of incomplete combustion in there because they don't have enough oxygen reaching the engine, the car engine. We also have kitchens at home. Sometimes we may forget to open the windows or the doors, and when we do that, we will be having less oxygen or less air circulating in the room, causing what we call incomplete combustion. Now, let me bring you to the attention. We said that carbon dioxide could cause global warming, but the damage carbon monoxide can cause is much worse than simply global warming, which may be having long-term effects. Carbon monoxide is actually a very poisonous gas. This is a very poisonous gas. How poisonous? Carbon monoxide will always combine with hemoglobin in the blood to form what we call carboxyhemoglobin. This carboxyhemoglobin is a permanent compound which will prevent oxygen from combining with this hemoglobin to form oxyhemoglobin. It therefore means that it will prevent the transportation of oxygen to the respiring cells, which may lead to suffocation and finally death. So it is advisable that when you are cooking with anything that has carbon, it could be charcoal, or these Lpgs. Lpgs are the gas cookers that we have at home. Those sources of heat like Lpgs or charcoal or even firewood here, we need to ensure we open the doors and the windows to ensure ventilation in the room so that we prevent incomplete combustion from taking place. In this case, we are just seeing carbon monoxide, but I said some carbon are also going unburned. So that is very, very dangerous for our health. So viewers, have explained to you the incomplete combustion and complete combustion. I've used the example of ethane, but as I've said, you can write the equation for the other alkanes. The products are the same. We said initially that all members of the same homologous gas series have the same chemical properties. So it means combustion, the products will be the same whether you are burning decane, we are burning ethane, we are burning pentane, we are burning methane, and so on. Now I want to come to the second property, which is substitution halogenation. Now halogenation is the reaction between alkanes and halogens. And like we said before, alkanes are unsaturated. Being unsaturated make them relatively inert to the other hydrocarbons like alkenes and alkynes. So it means that these reactions must be supported by some kind of energy. So we have substitution halogenation. We are also going to have what we call addition halogenation and substitution. Addition halogenation, we will find them in alkenes and alkynes. substitution reaction are found in alkanes. Now we said if I draw this one as ethane. Ethane is here, and we are reacting ethane with bromine. We are reacting ethane here with bromine. Bromine is Br. Now, this bromine here, we said that this alkane here is saturated. We need to substitute. So if one bromine has to come here, we need to swap. We need to exchange. One to go where that one is coming, another one to come here, because all these bonds are used up. There's no free bond where we can simply come and add. And we know that these carbon atoms must only have a total of 4 covalent bonds. They cannot have 5. And already those 4 are already used. This one is bonding this hydrogen, this hydrogen, this hydrogen, this is bonding this other carbon. So it means that the only thing we can do here is to substitute, to swap. Sometimes people, we swap our lines. If your line get lost, you tell them I want to swap. You tell them I want to change. I want to change because the other one is old. You want to swap because in school sometimes students have exercise books. Some schools give students exercise books. Now you use an exercise book, is get filled up, and then you go to the person in charge, you tell them, please give me another book. The other one is old. You are substituting. Although in this case they will leave for you that one that we have used by certifying that actually you have used it. So they are replacing it for you. So in this case also we want to ensure that for this bromine to come here, we are going to ensure that when we bring it here, this hydrogen here will go where that one came from, because they cannot all stick here. There's only one bond and you can only have one at a time. And this one, usually there's something we call monosubstitution. What I mean by monosubstitution is means that it can only substitute one at a time. Monosubstitution. Only one atom can be substituted at a time. It means I cannot take these 2 atoms and substitute them at once. That is not going to happen. It must be one at a time. So it means that in one instance here, what we can simply do is take this bromine here and that hydrogen here. That the first step of the reaction is done. So if I have, this is what we'll have. This is Br, this is H. So we have substituted one. The product here, the hydrogen will go there, so it will be H, Br. If I write a chemical equation here for this reaction, it means that if I have ethane, let me start by word equation, ethane. This one was ethane. Then we are adding bromine. So we add bromine. What do we form? We form this compound. Now we know how to name this compound. We know that it's on the first carbon atom. Whichever way, it will always be the first because we have only 2 carbon atoms. So in this case, we are allowed to just use bromoethane, or you can use 1 bromoethane. If I use 1 bromoethane only here, 1 bromoethane and bromoethane is the same. The problem only starts at 2 bromo. That's where you have to really make sense of it. Because even if I take this carbon bromine here, it is still going to be 1. So I can say this is, let me add just 1 bromoethane. Plus, this one is hydrogen bromide. Hydrogen bromide. So viewers, you see what we have done here. If you now write chemical equation, it will be C2H6. This is a gas, of course, plus bromine. You know bromine is a liquid at room temperature. To give us 1 bromoethane will be C2, this one, 1, 2, 3, 4, 5. 5 Br plus H Br. It's a gas. It's a gas. Now you see, viewers, this is what we have. And as you can see, it's fairly a simple case where we are substitution here. There's no way we can take this Br and write Br here. That will be wrong. Wrong. We cannot substitute at the same time. It must be mono substitution. or you can only substitute one hydrogen atom at a time. It means that if I want to substitute another one, I will go for the next equation, where this is going to be my reactant now, and I'm adding bromine. So I will now have C2H4Br2. I will continue like that until I remove all the hydrogen. But one thing has to happen. It must be step by step. That's what we call mono substitution. Now, this reaction here, this substitution reaction here, it must only occur when there is some energy which we call here light energy. Light energy. This light energy, we can simply get it from the sun. So we are going to call it UV light, ultraviolet light. Ultraviolet light. In exam, you are allowed to write UV light from the sun. It means that this reaction will not occur in the dark. If you try to do this reaction at night in your room, you realize you are not going to see a change. And how can you tell a reaction has taken place? Bromine here is orange in color. Some will see orange, some will see brown. So if you do it in the light, you will see the orange color quickly decolorizes, telling you that actually the substance which was brown in color, which was bromine here, has changed into something that is no longer brown. And that thing is now 1-bromoethane. But when you do it in the dark, you realize that you will continue seeing the brown color, which tells you that bromine or that brown substance did not react. That's why you still be able to observe it. So you have to really be careful when you are trying this particular test. When you put it in the dark, you see the orange color is just there mixed with the ethane there. You are seeing the brown. The moment you expose that container to the light, that orange color quickly disappears, telling you that something has happened. And it has happened because the reaction needs this UV light. Why do we need that UV light? UV light is needed to overcome the bonds between the halogen molecule. For example, bromine-bromine. We know that bromine is, they have equal electronegativities. It means that this is a purely covalent bond, which actually is very strong. So for it to react with something that is saturated, like we said that alkanes are saturated and they are relatively inert, we need to do away with this bond here. This bond, we need light or UV light to break it. So this is one of the reactions that require photocatalysis. See, it's photocatalyzed. Photocatalysis. Photocatalysis, one of them is this, another one is photosynthesis. Those are reactions that require light energy. One of them is substitution halogenation. So, what is a substitution reaction? A substitution reaction is a reaction in which an atom or a set of atoms is substituted with another atom or another set of atoms. Substituted, replaced. We need to use another word. If you use substituted, we can say replaced. Just like in a football match, we can't have 12 players or 13. So we just have to take one out and bring one in so that the number is maintained. Just like in this, the carbon atoms are, the carbon bonds are 4. So we just need 4 bonds to be used up. Once they are used up, to add one thing, we need to remove what already exists. Removing that and putting another one in its place is called substitution. If I have ethane here, ethane is a gas reacting with chlorine. Chlorine is also a gas. We said that it is mono substitution, meaning we can only remove one. We can only substitute one at a time. There's not football match where you can substitute 3 at once. You can only take one out at one point. So we'll take one chlorine here to substitute one here. That hydrogen will take place where that hydrogen came from. So it will be CH. It was 4. If you remove one, you remain with 3. So CH3, you bring one chlorine, Cl plus. Whatever remains there, one chlorine remain there, plus one hydrogen from the other side, we get hydrogen chloride. So this one here is a gas. This one also is a gas. This is a gas. You realize this is too easy, we don't even need to balance. So if you say here, this is methane, this is methane, this is chlorine. This one is chloromethane. We don't need to say one chloromethane because there's only one carbon here, and this one is hydrogen chloride. Hydrogen chloride. So sometimes in exam they'll give you two equations. One, you see one here and two products here. The other one, you'll only see one product. Where there's only one product, that's additional reaction. Where there are two products, that's substitution reaction. And we are going to see this question again when we do alkenes, especially this, what we call addition, addition halogenation. We are going to see again what that really means. Now, what are you going to be asked? One of the things you are going to be asked in this question is to state the type of reaction. The type of reaction is substitution reaction. That's the type of reaction. You realize that the word halogenation here may not really mean a lot, but it will just be telling you that what you are substituting is halogens. But the main name is substitution reaction. That's the key thing. The condition needed for this reaction to take place is UV light. That you must indicate when you are writing a chemical equation that this reaction can only take place in the presence of UV light. What about if you're reacting butane? Butane is C4H10, and you're reacting with bromine. Bromine, let me say chlorine. This one there. We said that just remove, you substitute one hydrogen. We said you can only take one out. So it will be take one hydrogen, bring one hydrogen, take one chlorine, bring here. So it will be C4H, take one, you have 9, Cl. Then plus HCl, which is a gas. So we have a gas here, a gas there, a gas there, and UV light there. So sometimes to illustrate what happens when we make what we call tetramethane, you have to do this process, the one we started here, assuming this is step 1. We said we have to do what we call monosubstitution. So once you substitute one hydrogen, you go for the second step where you're going to substitute the next hydrogen, because it must be mono substitution. So this is our reactant now. After substituting that one, that's our reactant. So we get CH3Cl, then plus chlorine again. So when we have chlorine again, what happens? We bring another chlorine atom, remove one hydrogen, so the hydrogen remains 2, and that hydrogen goes there. So it will be CH2Cl2 plus HCl. Again, we want to remove another atom. So we again continue to the next step, because we said it's monosubstitution. We cannot do all of it at once. So we carry this one, and we say CH2Cl2 plus another chlorine molecule. We again remove one hydrogen. So it will become CHCl3 plus HCl. Then we remove the final hydrogen, CHCl3 plus another chlorine molecule. We remove the final hydrogen atom, so you get CCl4 plus HCl. Viewers, this is up to 4 steps. Each step is removing one hydrogen, and that's what we have to know. We cannot simply say CH4 plus Cl and then you remove at once. You can only do that if you have in mind that that reaction went through 4 stages. Although you cannot see these 4 stages taking place, because if you take chlorine gas in a container, then you add methane gas again, and you start you reflux them, you mix them there together. You don't know these steps the way they are taking place, but theoretically this is what is taking place in that particular tube. Until the end of the day, you are going to find these particular compounds. This one was chloromethane. This is dichloromethane. This is trichloromethane. This is tetrachloromethane. They are formed in each stage of this particular reaction. Now, viewers, what is the precaution you should take in this particular reaction? If you are doing this reaction at home, you have to know when you are doing this reaction wherever, whether it's at home or in the laboratory, that these halogens are poisonous. Halogens are poisonous, whether chlorine, fluorine, iodine, and so on. They are poisonous, and therefore this reaction should be carried out in a fume cupboard. That is very key to note, because in every question examiner can ask you what is the precaution you should take, or what is the danger of doing this reaction. You must know the danger that is here. It is the halogen. It is dangerous, and you need to protect yourself by carrying out this reaction in a fume cupboard. Now, viewers, we have looked at substitution reactions, and we have said that this reaction requires light to take place, and the light commonly we can use is UV light that we have. That's the condition only that they need. It means that this reaction cannot take place in the dark. That UV light is required to break the forces of attraction of the covalent bonds holding the atoms of the halogens, whether it's bromine or chlorine or fluorine or iodine. The other thing we have seen is that this reaction is a substitution reaction, and it is a mono-substitution reaction for that matter, meaning we can only remove one hydrogen atom at a time. We cannot remove 4 of them at once or 2 of them at once. It must be one after another, and that's why we have these 4 steps here. And I've said that when you react these alkanes with halogens, you get what we call halogenoalkanes and hydrogen halides. That is a general equation that we can have. Alkanes plus halogens, what do you get? Some people call it halogenoalkanes, some say haloalkanes. So it is up to you to choose which one do you want to use. Haloalkanes plus hydrogen halides. Hydrogen halides. Halides are actually the halogens which have gained electrons, meaning they are ions in their nature. So viewers, finally I want to talk about uses. I want to talk about uses of alkanes. We can't get better uses than what we already know. We have talked about alkanes being used as fuels for cooking. So basically alkanes are fuels. That's the main word. Alkanes, if I say uses of alkanes, the main use of alkane, from which other uses may just originate, is alkanes are used as fuels. Then you can start looking at what fuels. Fuel to do what? We can talk about fuels for heating. Fuels for heating. Fuels for heating. Heating what? Heating food. Let me say heating stroke cooking. There's a fuel. Another use of these fuels is for lighting. Lighting, like home lamps and so on, like kerosene. Kerosene is alkane. It is used for lighting those lantern lamps we have. We can also use them as fuels to drive engines of cars. For example, gasoline, cars, fuel for cars. Let me say fuels for. So we can have cars, we can have generators, we can have ships, we can have power stations, and so on. We know diesel, we know kerosene, we know gasoline. All those we are going to look at under the next part of this chapter called crude oil. That's the next chapter we are going to talk about. So you realize that that is where we have this particular uses. You are going to find them there, and those basically are simply alkanes. We have also making road surfaces. Making road surfaces, especially for bitumen. Making road surfaces. This is actually the residue. Road surfaces. Those tarmac roads. So we are going to see we have alkanes. We can also talk about alkanes making alkenes, because sometimes we need to crack alkanes to make alkenes. That means that actually alkanes are not directly used. For example, you talk about making plastics. You make plastics from alkenes, not alkanes. But for you to make alkenes, you crack alkanes. So it means that in that particular case, we are not using alkanes very directly, but we are using it as a raw material for the next substance that we need. So basically, I will stop here by saying these are the main uses, and anywhere alkanes will be used as fuels. That's what you need to understand today. Fuel, it could be used in gas form, gas cookers that we have at home. It could be used in liquid form. We have kerosene, we have gasoline. It could be used in solid form, where we have used like making road surface like bitumen. We are going to see that in the next sub-chapter, that is crude oil or crude oil refinery. So viewers, today, so far we have done alkanes. We have finished with every aspect of alkane here. What is remaining under alkanes is just understanding the sources or currents of alkanes. Where do we get alkanes? And where do we get alkanes? We are going to answer that question in our next chapter, that is crude oil. Thank you, viewers. Please visit our channel, subscribe to us so that you can simply help us grow, even as we help you to learn from home. Thank you very much.